Welcome to the lesson on right-angle triangle theorems. In this lesson, we will discuss theorems that are specific to the right-angle triangle and how we can use them to prove triangles congruent or otherwise. Now here we have a right-angle triangle. And of course, we want to recall that a right-angle triangle is a triangle with a 90-degree angle. Now special rules like the Pythagorean theorem apply only to right-angle triangles. And remember that when it comes to congruence, we can sometimes use less information to show that two right-angle triangles are congruent than we would if we had two normal triangles. So one of the first theorems that we can look to try and prove is called Hypotenuse Leg. Now let's say that we have two right-angle triangles. They both have two corresponding right angles, two corresponding sides that are congruent, and then, of course, the two hypotenuses of each triangle are congruent. Now we have this proof here with 9 statements and 9 reasons, but sometimes it may be more helpful for us to take the two triangles and simply rearrange them so that it may become easier to interpret or to see some of the reasons that we will use to prove our statements. Now recall that within geometry, we are very much allowed to move figures without changing their sides and angles, and those figures remaining exactly the same. In this case, we've moved the triangles so that their hypotenuses are adjacent to one another. Now, taking a look specifically at this new figure we've created, I know that these two sides, A prime and C prime, and A prime and C are congruent. And because those sides are congruent, angle 1 has to be congruent to angle 2. Now, going back to the original shape, I know that angle C and angle C prime are both my 90-degree angles. And because they are both my 90-degree angles, the other angles that are part of those 90-degree angles, angles 3 and angles 4, must also be congruent as well. Now that I know angles 3 and 4 are congruent, the sides opposite those angles, CB and C prime B prime, have to be congruent as well. Now I have two pairs of sides that are congruent, but remember that these two triangles share the hypotenuses. Therefore, these two triangles end up being congruent due to the theorem of side, side, side. Now, what if I have other conditions? I can begin to think about if I have the hypotenuse of two right-angle triangles and an angle. So I have two triangles here, and again with another proof that I can go through and look and see that if I can determine these two triangles are congruent just by looking at the hypotenuse and of course an angle that's not included. Now, every right-angle triangle already has an angle that's 90 degrees. So if I have another pair of angles that's congruent to one another, the third remaining angle also has to be the same because both triangles have to add up to 180 degrees. Now that I have a third pair of congruent angles, I essentially have an angle pair at the top, an angle pair that we've already established, and a side between them. So these two triangles end up being congruent because of side angle side. I don't even necessarily need to use the 90-degree angle in this particular case. Now let's go ahead and apply some of these theories into practice and solve some of these problems correctly. In this first problem, I need to go ahead and find the length of CB, so not the entire hypotenuse, but just part of it. Now these two sides are denoted as being congruent, so they are both 4 root 2, and I'll use both those sides to set up the Pythagorean theorem equation. So 4 root 2 squared plus 4 root 2 squared should equal AB squared. So AB squared will end up being equal to 4 root 2 squared ends up being 32 after each and everything is squared. So AB squared is 64 and AB is 8. So if the entirety of AB is 8, CB should end up being just 4 because CB will be half of that hypotenuse. Now if I'm trying to find the perimeter of the quadrilateral in this next problem, I'm reminded that because these sides are equal, I can set up that 3x should equal 5x minus 4. After using some algebraic properties, I get that 4 equals 2x and that x equals 2. So I go back to my problem and I plug in x, and I get that AB should equal 6. And without necessarily having to plug it in, I know DC should equal 6 also. But now I don't know AD or BC, so I again will use the Pythagorean theorem and set up that 6 squared plus 8 squared should equal BC squared or AD squared. In this case, I could use the variable z. So I add up the other side and I get that z squared equals 100 and that z equals 10. So now after adding up all the sides together, 10 plus 6 plus 6, we should get a total and final perimeter of 32. Next, let's take a look at various pairs of right angle triangles and see if we have enough to determine that these two are congruent. So in this first pair, I do know I have congruent hypotenuses and a pair of congruent corresponding angles. But I don't know if I have a right angle. I don't know if these are even right angle triangles. So because of that, I can proceed no further. I just know I have a side and an angle. That's it. That's not enough to prove any type of congruence. In this next example, I do have a pair of right angles and another pair of congruent angles, but are their hypotenuses the same? Two pairs of angles will guarantee the third, but there's no guarantee about the sides of any of those sides. In the last example, I have the two hypotenuses that are the same and the two right angles are the same, but no guarantee of any other matching angles. So even though the hypotenuses are the same, the triangles can have any particular shape.